in the course so far we have studied many properties of groups. Most recently we have looked at isomorphism theorems, quotient groups, and as an application of these we have studied the Cauchy's theorem, which says that if a finite group has order n and you have a prime number that divides n, then there is an element of that prime order. Okay, the next important topic in the course is symmetric groups. I'm going to spend this and probably the next video studying symmetric groups. Okay, we have already looked at symmetric groups as an example, and we looked at one of these groups in detail. So what are symmetric groups? Let's recall. So let n be a positive integer. Okay, so let n be a positive integer, and we denote the symmetric group on n letters by Sn. So Sn denotes the symmetric group on n letters. What does this mean? Okay, so this means the following. So we usually give the letters we call by 1 to n. So Sn is the group of all bijections of an n element set. So you take a set with n elements and you consider all bijections of that set. Usually we denote the set which has n elements. When I say n element set, I mean a set having n elements. It has n elements, right? It's very natural to give names to these n elements. Let's call them 1, 2, 3, 4 up to n. So these are the n elements. Don't think of them really as numbers. It's sometimes useful to maybe think of them as numbers, but the point is there are n elements in that set which we are denoting for convenience as 1, 2, 3 up to n. Right? So we already are familiar with S3. This is one of the groups that we have been looking at in various situations, and we saw how many elements it has and so on. So for example, what is the order of S3? 6. And we have various ways of writing this. So I introduced in the very beginning one notation where I called the elements right. So I called maybe I called them F1 through F6, and this we thought was not very useful. It's not convenient because we don't know what F1, F2 are. We have to go back and see what they are, and because of that I introduced a notation, and we will discuss this in more detail today. This notation that I introduced right. So I'm going to spend this video explaining how to understand Sn and what this notation is and what are its properties, and we will consider some basic properties of the symmetric group. So symmetric groups, remember, are just not one group, it's a class of groups. For every positive integer we have one group. For example, let's quickly settle what S1, S1 and S2 are. What would be S1? S1 is by definition bijections of a one element set. So, and what are they? There is only one bijection, right? There is only one bijection from a single element set. Remember, we call the element 1. There is no surprise here. 1 has to go to 1. So it is the identity bijection. Remember, E denotes the identity element of the symmetric group, and as a function this stands for the identity map, which is definitely a bijection. And I should remark here, of course, that when I say group of all bijections, I mean under composition. Way back in one of the first videos, we saw that bijections under composition form a group. So the binary operation in this group is composition. Every bijection has an inverse. Identity bijection serves as the identity element, and composition of two bijections is a bijection. So this is a group under composition. So S1 is the trivial group, just containing one element. What about S2? So we have to look at bijections from 1 2 to 1 2. Right? So there is the identity bijection. So 1 goes to 1 and 2 goes to 2. This is there always. And we have another bijection which sends 1 to 2. In order to be different from this, 1 must go to something different from 1. So 1 goes to 2 and 2 goes to 1. Right? So let's call this 1 2 following our notation. I'm going to recall this again for you later in the video. 1 2, remember, is the bijection that sends 1 to 2, 2 to 1. And there are no other elements here, no other letters here. So it is just E and 1 2. And of course S3 I have written here is these 6 elements. So the first thing we want to understand is, and of course S4 will have more elements, it will be bijections of 1 2 3 4, and S5 will be bijections of 1 2 3 5, 1 2 3 4 5, and so on. So first thing is, first question, let us settle this first. What is the order of Sn? Okay, so here we are looking at bijection. So it's a simple set theoretic count. So Sn is all bijections from 1 2 up to n to itself. Right? So these are bijections. Let's think for a minute on how to construct a bijection. Bijection is a function, right? Bijection is a function which is 1 1 and on 2. So 1 has to go to something, 2 has to go to something. Similarly, 3 has to go to something. Finally, n has to go to something. First, let's see how many options there are for 1. There are n options. Right? Because 1 can go to 1, 2, 3 or n. It can go to any of the n letters. So there are n options. Now how many options are there for 2? Now for 2, remember, in order to be a bijection, 1 and 2 being distinct letters must map to distinct letters. So we have made a choice for 1 in the beginning. 2 cannot go to that. So if 1 goes to 2, 1 goes to 3 for example, 2 cannot go to 3. But 2 can go to anything else. So you remove wherever 1 has been sent, and 2 can go to any of the remaining ones. That means there are n minus 1 options on where n 2 can go. 3 now can go to any of the letters which are different from images of 1 and 2. So 3 has n minus 2 options, 4 has n minus 3 options, n, finally after you do all this, there is only one option for this. And this is the principle at work. If you remember how we worked out S3, S1, S2. Okay, so you can send 1. So 1, 2, 3 up to n is an arbitrary order. We fix them in some way. Which order is irrelevant. It's convenient to think of 1 as the first element, 2 as the second element, and so on. So 1 goes to any of the n options, 2 goes to any of the remaining n minus 1 options, 3 goes to any of the remaining n minus 2 options, n goes to, after having decided the images of 1, 2, 3 up to n minus 1, we have exhausted n minus 1 elements of the set 1, 2 up to n. So there is only one option left for n. Now how many there are total? So this is a principle in counting. If how many total number of bijections are there? So the total number of bijections because 1 can go to n of them, it is n times 2 can go to n minus 1 of them, 3 can go to n minus 2 of them, n minus 1 go to 2 of them. So this is the product. Okay, so n minus 1 times n minus n times n minus 1 times n minus 2 all the way up to 2 times 1, and we usually call this by n factorial, right? Read this as n factorial. So the total number of bijections is n factorial because where you send 1 is independent of where you send 2, apart from making sure that 2 has to go to something that is not already the image of 1. So once you keep that in mind, 2 can go to anything. So you can fix one of the options for 1 and you can construct a function. So now change the option for 1 and construct same number of functions and so on. So the total number of bijections is n factorial. Hence the order of Sn is n factorial. So this is the first important property of Sn. Sn is a group of order n factorial, and clearly check that this checks out in cases 1, 2 and 3. S1 should be 1 factorial, which is 1, and that's correct. S2 should be 2 factorial, which is 2, which is also correct. S3 order must be 3 factorial, which is 6, which is correct. So Sn is a group of order n factorial. Okay, so and the size is increasing, right? It gets very big very fast. For example, S4 has order 24, S5 has order 120, S6 has order 720, and so on, right? So these orders increase very fast because each time you are multiplying by n. Okay, so this is the size of the group. Now how do we express elements of Sn? So this is the next question. How do we express elements of Sn? So there are several ways of expressing elements of Sn. We want to choose one which is most convenient in the sense that it is efficient, we don't need to write a lot of text, and it's easy to work with in terms of multiplication of elements, in terms of figuring out whether an element is in a subgroup, things like that. Okay, so how do we express elements? So I want to introduce to you, and this is actually introduced to you when we discussed S3 earlier, but I will do this again in more systematically. We use cycle notation. Okay, so hopefully this is already familiar to you from the time we discussed S3. So, and in any case I will discuss all the details again. So what is a cycle notation? So it is best explained in terms of with an example. So let's look at for example, let's start with this. Okay, so before I do the example, just a notation so that I can keep using this. Elements of Sn are usually permutations. Okay, instead of using the word bijection, let's use the word permutation. Permutation is just another word really for bijection. It's about if you take n elements, how do you permute them? How do you map those n elements to themselves again? So that's really a bijection. But this is a more mathematical term, so we use the word permutation. So let's take a permutation, and I'm going to denote this by sigma. I'm going to use these Greek letters. So sigma is an element of S9. So it's a permutation on n letters. Okay, what is this? So let's use one particular way of writing this. So let's use this notation. So let's use this as a matrix, represent this as a matrix where the first row has all the 9 elements of the set 1, 2, 3 up to 9. So sigma is a permutation of it. So sigma sends 1 to 3. Let's do this 2 to 4. So The top row represents the letters, the bottom row represents where they are mapped under sigma. So sigma maps 1 to 3, 2 to 4, 3 to 2, 4 to 1, 5 to 6, 6 to 5, 7 to 8, 8 to 7, 9 to 9. Okay, so this ends, for example, 3 to 2, 6 to 5 and so on. Okay, I hope the notation is clear. 1 goes to 3, 2 goes to 4 and so on. So clearly this is nice, clearly it tells you what element sigma does, in the sense that what is the function. Remember, elements of Sn, which I am calling permutations, are really functions. They are functions from 1, 2, 3 up to n to 1, 2, 3 up to n. So in that way sigma is clear, what as a function it does is clear. 1 goes to 3, 2 goes to 4. But certainly you can see that there is some inefficiency in expressing sigma. For example, the top row is unnecessary, because we know that it's always 1, 2, 3 up to n. So, but if you remove that, it's somewhat difficult to keep track of what the function is. So now rewrite this in the following way. Rewrite sigma in the following way. So what is the way that we want to think of sigma? Is the following. So let's start with 1. Okay, so I can start with anything. Let's start with 1. See where it goes under sigma. Okay, so I'm starting with 1. See where it goes. It goes to 3, right? And see and repeat till, so let me write that first. Okay, so see where it goes under sigma. Put it next to and repeat until we come to 1 again. Okay, so that's what we do. So let's illustrate this. We start with 1. See where it goes to 3. Repeat with 3. So see 3 goes to 2. It's right there, right? The function sends 3 to 2. We have not come to 1 again, so we continue. 2 goes to 4 under this. So again we have not reached 1, so continue. Where does 4 go? 4 goes to 1. Okay, so 1 we have come again, so we close the bracket. So this is the, we call this the cycle determined by 1. We call this the cycle determined by 1. Again repeat, let me repeat the procedure. We start with 1, see where it goes, put it next to it, so 3. See where 3 goes, it goes to 2, so put 2 next to 3. Where does 2 go? It goes to 4. So put next to 2, you put 4. And 4 goes to 1, so you close the bracket. So you should think of this as a cycle. So because you start with 1, you go clockwise, you go to 3, then you go to 2, then you go to 4, and then you come back to 1. Okay, so of course in this whole thing can start with 2 also. If we started with 2, what happens? We start with 2, see where 2 goes. 2 goes to 4, 4 goes to 1, 1 goes to 3, 3 goes to 2. So we close the bracket. It is the same cycle. Right? It is the same cycle, because instead of starting on a circle, it doesn't matter where you start, right? Instead of 1, I'll start here. 2, 4, 1, 3. Similarly, if I started with 3, it will be 3, 2, 4, 1. If I started with 4, it will be 4, 1, 3, 2. So this is the, of course, this is one cycle. Sigma is not just this. So now in the next step, so this is the step 1. Step 2, find an index if that is not contained in the cycle determined by 1. Find an index. So let's call 1, 2, 3 up to n indices. Okay, so the set is 1, 2, 3, n. Elements of it are called indices, and elements of the symmetric group are called permutations. So permutations permute indices. So find an index that's not contained in the cycle determined by 1. So 1, 3, 2, 4 are contained in the cycle. Let's pick 5. So choose 5. You can also choose 6, or you can also choose 7, it doesn't matter. So I'm just choosing 5. Now find the cycle determined by, right? So in general we have learned in the step 1 how to determine the how to find the cycle determined by an index. In this case, let's do it for 5. You put a bracket and start with 5. Under the function, where does 5 go? 5 goes to 6. Right? Now where does 6 go? 6 goes to 5. So I close the bracket. So I get 5, 6. So it is a cycle. 6, 5 goes to 6, and 6 goes to 5. So next, you see what now happens. Find an index not contained in the cycles constructed so far. So remember, so far we have constructed 2 cycles, 1, 3, 2, 4 and 5, 6. So find an index that's not contained so far. So let's choose 7 and determine the cycle. Find the cycle determined by 7. It would be 7, and in the function, what is the image of 7? 7 goes to 8 and 8 goes to 7. So you take 7 goes to 8 and you close the bracket. Okay, so this is the third cycle, and last cycle will be find the cycle. So again, it's the same idea now. Find an index not covered so far, which is only 9. 9 is the only index that's not covered so far, and the cycle determined by 9 would be, in the function 9 goes to 9. So you just use you have only 9 in the cycle, so you have a single element. So we say that we can write sigma equals 1, 3, 2, 4 was the first cycle, 5, 6 was the next cycle, 7, 8 is the third cycle, and 9 is the last cycle. We usually don't write a cycle if it has only one index. Okay, because if it has only one index, it is clear that that index goes to itself. So we usually omit writing 9. So we write as sigma as 1, 3, 2, 4, 5, 6 and 7, 8. So the same function, the same permutation that we had here has this cycle decomposition. This is called the cycle decomposition. Cycle decomposition of sigma. So what are we doing? We are decomposing sigma as cycles. So a cycle, first of all, is an element which starts somewhere and ends with that. So 1 goes to 3 in this cycle, 3 goes to 2, 2 goes to 4. So cycles are permutations of the form. So now let me introduce a general notation here. Okay, so this is a cycle. It has k indices. So this is a k cycle. So we call it a k cycle. What is a k cycle? It is a cycle with k indices. What does this k cycle do? What does the k cycle 1, I1, I2, I3 up to Ik do? It sends I1 to I2, I2 to I3, I3 to I4, right? You understand? I1, the first thing, goes to I2, which is right next to it. I2 goes to I3, which is right next to it. Right next to I3 is I4, so I3 goes to I4, and so on. Ik minus 1 goes to Ik, because Ik minus 1 comes just before Ik, so Ik minus 1 goes to Ik, and finally, where does Ik go? Because it's a cycle, you cycle back. There is nothing next to Ik, means you send Ik to I1. So as a cycle, you have I1, then I2, always clockwise, I4, I5, Ik minus 2, Ik minus 1, Ik. Right? So I1 goes to I2, I2 goes to I3, I5 goes to I6, I6 goes to I7, Ik minus 1 goes to Ik minus 2 goes to Ik minus 1, Ik minus 1 goes to Ik goes to I1. So this clearly says that this same cycle can be written as I2, I3, Ik minus 1, Ik, and I1. Right? So you can start with I2 and end with I1, and you can write them in any of these options. You can start with I3, you can choose any of the k indices as the starting points. But now the description of the cycle is not done. I have only told you what happens to these indices. Further, I need to tell you what happens to indices that are not in this set. If J is an index not contained in see I1, I2, Ik are just some indices which are, remember, this is a subset of, so if Ij is an index not contained in this I1 through Ik, what does the cycle I1, I2, Ik sends? J to J. It doesn't do anything to J. Now I have completely described the cycle, right? As an example, consider the cycle, let's say 1, 2, 3 in S6. What does it do? As a function, one, two, three is given by S6 is the symmetric group on 6 letters, which are 1, 2, 3, 4, 5, 6. I need to tell you what is the image of each of those indices under 1, 2, 3. 1 under 1, 2, 3 goes to 2, 2 goes to 3, 3 goes to 1. So all the indices contained in the cycle behave this way, and all the indices that are not contained in the cycle are fixed. Okay, so we say 1, 2, 3 fixes 4, 5 and 6. So it fixes them. So a cycle More generally, cycle I1, I2, Ik fixes any index that's not contained in I1, I2, Ik. Okay. So now going back to the example that we worked out here, this particular permutation sigma can be written as a product of cycles 1, 3, 2, 4, 5, 6 and 7, 8. So in our example above, sigma which was in S9 can be written as a product, okay, of disjoint. Okay, let me explain this in a minute. Can be written as a product of disjoint cycles in the following way. We worked this out, right? 1, 3, 2, 4, 5, 6, 7, 8. These are disjoint cycles because they have no common indices. Right? The indices that 1, 3, 2, 4 contains are 1, 3, 2, 4. 5, 6 contains 5. 7, 8 contains 7 and 8. 5, 6 contains 5 and 6. So there is no common index. So they are disjoint and they are cycles. So sigma can be written as a product of disjoint cycles. Now, if you think about the procedure of how we did this for this particular sigma, hopefully it will be clear to you that we can do this for any sigma. The same procedure, that we used for sigma in S9, the same procedure can be applied to any element sigma in any symmetric group. So we can conclude a proposition. Every element sigma in a symmetric group has a cycle, has a decomposition as a product of disjoint, right? So remember, this is clear because you start with sigma, ask where 1 goes. So I'm just recapping the procedure that we followed. Start with 1, determine the cycle determined by 1. So you start with 1, see where it goes. You put it next to 1. See where that goes. Put it next to that, and so on. You keep repeating. At some point, you obviously will reach 1 because Sn is a symmetric group on n letters. Only n indices are there. So you cannot keep forever going without reaching 1. So at some point, we must reach 1. Then you close the bracket, and that's the cycle determined by 1. Maybe you exhausted all indices. Then you have a 9 cycle. All the 9 indices are in this cycle. Or maybe you have not exhausted all indices. Sorry, all n is in general now. So it's possible that you have all n indices in one cycle. Then you are done. So the element itself is an n cycle. Otherwise, there is an index that's not contained in the cycle determined by 1. Then you start with that and see the cycle determined by that. And you keep doing this because it's all on n letters. You must have at some point exhausted all the indices. So you're done. So every element of Sn has a decomposition as a product of disjoint cycles.